Welcome. So what we're going to show you today is how Alice and Bob are going to exchange a message between one another, but also keep it secure. So what we're going to do is we're going to use RSA's cryptography encryption tool, in which Bob is going to send a message to Alice without Eve being able to figure out what that message is. So the way we're going to do that is we're going to have Alice create a public and a private key. Alice is going to distribute the public key to Bob. Bob is going to encrypt a message, send it back to Alice, and Alice is going to use her private key to decrypt the message. So the first thing Alice needs to do is write down two random prime numbers and label them P and Q. So let's just say that Alice says P equals 11 and Q equals 13. Next, we're going to multiply these two numbers and label that N. So N equals P times Q, which equals 11 times 13. So N equals 143. That's going to be a part of her public key that she's going to share to Bob. Next, we're going to find the least common multiple of P minus 1 and Q minus 1 and label that lambda N. So lambda N is equal to the least common multiple of P minus 1 and Q minus 1. So in this case, it's the least common multiple of 1 less than both of these numbers. So it's going to be 10 and 12. And then you can use Python for this, and that will give you 60. Now we're going to write down a natural number between 1 and lambda n that has no factors in common with lambda n, and label that number E. So E needs to be between 1 and lambda n, and we're going to say in this case E equals 7. So if it has to be between 1 and 60, notice how these are relatively prime, meaning that they have no factors in common. And this is going to make up the other part of Alice's public key. So the public key is comprised of N equals 143 and E equals 7. Now, Alice also needs to come up with a private key that is not going to be distributed to Bob. And the way we're going to do that is we're going to find the modular multiplicative inverse of E and lambda n and label that number D. Let me do that here. So we need to find a number such that D times E mod lambda n is equal to 1. So in this case, D times 7 mod 60 equals 1. So again, you can use Python for this, and that is going to come out to be equal to 43, and this is our private key.
So just to summarize, Alice used the values of P and Q to create the public key, and then created the private key D. Now she's going to publicly announce the public key, so Eve can actually hear this public key being announced. So the next thing that needs to happen is that Bob needs to come up with a message. Now, Bob's a man of few words, so his message is just going to be 3. He doesn't have a whole lot to say. So once he has a message 3, he needs to actually encrypt this message. So we'll call that C of M. We're going to set that equal to m to the e mod n. Now we're going to plug in the values of e and n that were created by Alice. Now this is pretty easy to do in Python, as you saw from the previous math prerequisites. Just make sure that to do 3 to the 7th power, you do 3 asterisk asterisk 7. So when you do all this, switch markers here. When you do all this, you end up with the number 42. So now we have our encrypted message. Now, Bob is going to send this message back to Alice. And now Alice is going to use her value of D to unencrypt this message.
So, the way Alice does this is Alice is going to use the function m equals c to the d mod n, mod, not mod. So plugging in the encrypted message that Bob created, it's going to be 42 to the, and now this is where the private key comes into play. Eve has no idea what this number is, so Alice uses 43, mod n, which is public, 143, and you could use Python for this. You're going to come out to the original message of 3. So notice that unless Eve has both C and D as well as N, Eve cannot figure out what that message is. All Eve has access to is C and N, but not D. So Eve cannot figure out what that message will come out to be.
So essentially, Eve would need to guess some value of D that makes this message make sense, which in reality is actually not that easy. Also in reality, these numbers are much, much larger.